Hello friends, in this lesson we will talk about CNN or convolutional neural networks, and let's begin. Here we import the libraries, and here OS. What is OS? It interacts with the operating system and random, and I will pass, and either tools. What is this? It provides functions to create iterators for efficient looping, and NumPy, pandas, and matplotlib here. And let's look at this part: scipy, spatial distance, and pdist and sucarform. What is this? First, pdist and sucarform, it calculates pairwise distances and convert them to a distance matrix. And here the confusion matrix and classification report, that. And here Keras and Keras modules are important to build and train neural network models. And what we can say, I think it's enough. And here we read our data, PM train data here, and you can see the rows and columns here. And let's look at our visual, what happens here, and let's talk about. Here we set the figure size, that part. And let's look at this part: train df id value counts plot bar. What happens in the second line? It counts the number of occurrences for each engine id in the training dataset. And plot bar, it generates a bar plot of these counts showing how many cycles each engine has before failure. And then we'll print it. And here we can talk about our plots. Each bar represents the total number of cycles for a specific engine before it fails, and the heights of the bars vary significantly, indicating that some engines last much longer than others before failure. And the printed output shows the median working time of approximately 206.31 cycles, and this is the average number of cycles across all engines, and this value provides a central tendency measure indicating that on average an engine lasts about 206 cycles before failure, and the maximum working time is 362 cycles, meaning that the longest lasting engine in training set ran for 362 cycles before failing. And the minimum working time is here 128 cycles, indicating that the shortest lived engine ran for only 128 cycles. And this range shows a broad distribution in engine lifespans, highlighting the variability in the datasets. And let's talk about the importance of this analysis, why we do that. Knowing the range and distribution of the data helps in designing a model that can handle the variability and make accurate predictions across different scenarios. And by identifying engines with shorter lifespans, maintenance schedules can be optimized to prevent unexpected failures, saving costs and improving reliability. And this analysis provides initial insights into the dataset, helping to further exploratory data analysis and feature engineering. And let's look at our other parts and what happens here. And let's talk. Here, engine ID and traindf. First time, what happens here? This line filters the traindf data frame to include only the rows where the ID is 1, meaning it selects all the data related to engine 1. At x1 here, what happens here? It selects all columns from the third onwards, which correspond to the operation settings and sensor measurements. And here you can see the plot settings, subplot true, share true, and what we can say, sharing the x-axis, I mean here, and plus each selected columns as a separate subplot, and here the size. And we have a lot of plots here. What are they? And let's talk about. Oopsie, why it's switch? Okay, let's stop. These plots provide a detailed view of how various sensor readings and operational settings change over the cycles for engine 1 and operational settings. Here, setting 1, setting 2, and setting 3. And these settings often remain constant or very slightly, indicating stable operational conditions for the engine. And what we can say another for sensor readings, what we can say here, as you can see, S1 to S21 here. Each sensor plot shows how specific measurement vary over time. And for example, for instance, let me see. Okay, here S1 to S4, we can see some fluctuations here, as you can see, 2, 3, 4. Some fluctuations which might indicate changes in specific conditions like temperature, pressure, or vibration. And let's talk about S5 to S21. These sensors also have varying degrees of fluctuations which might correspond to different aspects of engine performance and health. And some sensors show stable readings, for example S3 and here S10, like that. And what we can say another other sensors exhibit noticeable fluctuations, and for example sensor 2 here and for example S4, and which might be critical in predicting when the engine is likely to fail. And such variations often signal stress or anomalies that could precede fault. And by observing these plots, we can identify patterns and potential anomalies. For example, if a sensor's reading starts to diverge significantly from its usual range towards the end of the cycles, it might be an earlier indicator of an impending failure. And I think it's okay. By the way, you should examine and look to everyone manually. But if I do that now, lesson will be long. So I switch and let's look at this part. What happens here? Actually, it's basic. We have a code block here, and these lines here reads the test data from a text file into a data frame, and data is space separated and has no reader. And test df drop, what happens here? Let's talk about the original dataset has extra columns that are dropped as they are not needed, and renaming columns here, id cycle setting 1, setting 2, etc. The columns are renamed for clarity corresponding to engine ID, cycle number, operation settings, and sensor measurements. And we will print them, and we will see the first 3 value here, and what we can say here, the test data frame has 100 engine, unique engine IDs with each engine's data splits across multiple cycles. And what we can say here, the dataset contains 13,096 rows and 27 6 columns indicating multiple cycles per engine, and I think it's okay. And what happens here, and let's talk about this code block. Here, this line reads the ground truth data, which indicates the remaining useful life of engine in the test set. And truth df drop, what is this? It drops the unnecessary column from the data frame and truth df columns more here. It renames the remaining column to more, indicating additional cycles after the last recorded cycle in the test data. And here, what is this +1, and what happens here? It sets the data frame index to start from 1, aligning it with the engine IDs, and we will print them. And you can see our output. The ground truth data frame contains 100 rows, each corresponding to an engine in the test set. The more column indicates the additional cycles each engine would have run after the last recorded cycle in the test data before failing. And I think it's okay. And let's look at our another parts, and let's talk about these two lines. What happens here? Here, train df rule equal train df group by and transform. We have two major function, group by and transform, and let's talk about group by ID here. What happens here? It groups the training data frame by the engine ID, and here cycle transform max. For each group, it finds the maximum cycle number, and which represents the cycle at which the engine fails, and train df cycles here the current cycle number for each row in the data frame, and transform max minus train df cycle. It subtracts the current cycle number from the maximum cycle number to calculate the remaining useful life for each cycle, and this gives the number of cycles remaining before the engine fails. And here this line prints the remaining useful life values for the first 10 cycles in the training data frame, and the remaining useful life values indicate how many cycles remain before the engine fails. For example, the remaining useful life for the first cycle, I mean index 0, 191, meaning the engine will fail after 191 more cycles from this point. And the rule for the second cycle, I mean index 1 here, is 190, indicating one last cycle remaining until failure. And the rule decreases by 1 with each subsequent cycle, which is expected since the engine is one step closer to failure with each passing cycle. And I think it's okay. And let's talk about the other code block and what happens here. Here we have some threshold, and W1 and W0. What are they? These lines define the thresholds for categorizing the remaining useful life, and W1 here, it engines with the rule less than or equal to 45 cycles are considered to be in the warning zone, and W0 equal 15, engines with rule less than or equal to 15 cycles are considered to be in the critical zone. And what we can say here, train df and label 1 and label 2, what are they? First, and let's look at this parse W1 and 1 and 0, and what happens here. These lines, this line with MP-var creates a binary label where 1 indicates the engine rule is less than or equal to the 45 cycles, and 0 indicates the engine's rule is greater than 45 cycles. And let's look at this part, terrain and label 2. What happens in these lines here? Sorry, here. These lines with these lines, it will be better. Okay, now you can see the seconds and here first. What happens here? These two lines modify the binary labels to create a ternary label, and to indicate the engine's rule is less than or equal to 15 cycles, and 1 indicates the engine's rule is between 16 and 45 cycles, and 0 indicates the engine's rule is greater than 45 cycles. And let's look at our scale parts and what happens here. First, df scale and return. And what are they? What happens here? This function normalizes a data frame column to the range, and range is 0, 1, using min-max scaling. And this ensures that all sensor data is on a similar scale, which helps in training the machine learning model. And we will apply them with that for loop. Here, this loop applies the scaling function to all columns in the trained data frame that start with S, which are the sensor measurement columns. And here, train df. What happens here? This line drops any columns that contain non-values, ensuring a clean dataset for modeling. And here, train df hat, it displays the first few rows of the process training data frame. And we have an output or a table, you know that. What we can say, the sensor columns are now scaled between 0 and 1, as you can see here, and making the data suitable for machine learning models. And the rule columns here shows the remaining useful life for each engine cycle, and label 1 and label 2 here. Columns categorize the engines based on their role. And I think it's okay, and we can continue to other parts, and let's talk about this part. What we can say here: truth, test df, and for loop. First, the truth df, and what happens here? The design calculates the maximum cycle number of each engine in the test dataset and adds the more column value from a truth df to determine the total cycle each engine would have run before failure. And here test df rule equal truth df max. And what happens here? Let's talk. This line, I mean second line, computes the rule for each row in the test dataset by subtracting the current cycle number from the total cycles to failure for the corresponding engine. And let's look at this part. What happens here? Design creates a binary label, and 1 indicates the engine's rule is less than or equal to 45 cycles, and 0 indicates the engine's rule is greater than 45 cycles here. And you know that label 2 parts again. 2 indicates the engineer's rule is less than or equal to 15 cycles, and 1 indicates the engineer's rule is between 16 and 45 cycles, and 0 indicates the engine's rule is greater than 45 cycles. And again, we have a loop here. And what happens here? By the way, we can remove that. Okay. So what happens here? This loop applies the scan function to all columns in the test data frame that start with S, which are the sensor measurement columns, and test df and test df hat with drop na. And again, what we can say here, Label 1 and label 2 categorize the engines based on their role, and label 1 here, binary classification indicating whether the engine is in the warning zone, and label 2 here, ternary classification indicating whether the engine is in the safe zone, warning zone, or critical zone. And I think it's okay. And let's talk about the sequence part. What happens here, and let's talk. First, sequence length equal 50. What is this? This sets the length of each sequence to 50 cycles. In the other words, each input to the model will consist of data spanning 50 consecutive cycles. And we have a function here, and it's named gene sequence. And what is this? This function generates overlapping sequences of sensor data and input id underscore df and sec length of each sequence, and sec calls, I mean columns, to include in the sequence. And what is the process here? It converts the specified columns into a matrix and uses a sliding window approach to create sequences of length 50. And for example, if an engine has 192 cycles, it creates sequences from cycles. And I think it's okay. And let's look at the generating labels part here. This function generates labels for each sequence, and here the parameters, and it converts the specified label column into a matrix and skips the first sec length rows to align labels with the end of each engine, I mean each sequence, sorry. And I think it's okay, so we can continue. And let's look at the here sequence columns and here cut blocks. What happens here? Here we have a loop, and this loop iterates through all column names in the train data frame, and it checks if the column name starts with S, which indicates it is a sensor measurement column, as you can see here. And it appends these sensor columns to the sequence underscore calls, I mean sequence columns list, and it will be print here. And the printed list of sensors columns shows the names of all columns that contain sensor data, which will be used to generate sequences for the model. And let's look at these parts and what happens here. Let's talk. Xtrain, xtest, and empty initializes empty list to hold the training and test sequences. And we have a loop here. By the way, we have a tree loop here, and what happens here? Let's look. It iterates over each unique engine ID in the training data frame, and for each engine it generates sequences using the gene sequence function and appends these sequences to xtrain. Similarly, generates sequences for the test data frame and appends them to xtest, x underscore test. And xtrain and xstat as array. What is this? It converts the lists of sequences into numpy arrays, which are more efficient for numerical operations and suitable for machine learning models. And we will print. And let's look at our output here. What happens here? The training set here consists of 15,631 sequences, each of length 50 cycles, and 17 features, I mean sensor measurements. And here the test set, I mean X test, consists of 8,162 sequences, each of length 50 cycles and 17 features. And why sequences? Let's talk about Sequences allow the model to learn temporal dependencies in the data, which is important for time series forecasting. And the model can identify patterns over time, such as gradual increases in temperature or pressure that precede engine failure. And I think it's okay, and we can switch. And let's look at this part. What happens here? Y-train, Y-test. Here, initialize this empty list to hold the training and test labels, as you can see here. And again, we have a tree loop here. It iterates our each unique engine ID in the training data frame. For each engine, it generates labels using the genLabels function and appends these labels to Y-train. Similarly, generates labels for the test data frame and appends them to Y-test. And again, MPS array, you know that part. And you can see here the new outputs. So I think we can pass. And let's look at this part, what happens here, and let's talk. Here we have a function recplot, and what is this? This function creates a recurrence plot, which is a way to visualize the recurrence of states in a dynamical systems. And what are the parameters or inputs here? As the input sequence, and apps. What is apps? A threshold parameter to control the granularity of the recurrence plot. And steps equal 10. What is this? The maximum value to cap the distances. And here pdist, what is this? It computes the pairwise distances between the elements of the sequence. And np floor and d and f's. What is this? It normalizes and it discretizes and the distances. And here let's look at this part, third line. It caps the maximum distance to the specified steps. And z equals square form d. What is this? It converts the distance vector into a square matrix. And output, this function returns a recurrence plot matrix. And here let's look at another part. This plot generates and visualizes the recurrence plots for each feature in the first training sequence. And peak size, you know that you can change the sizes. And it iterates over the 17 features, and for each feature it generates a subplot and calls recplot to generate the recurrence plot for the feature, as you can see here. And display the recurrence plot using plot imshow here. I mean imshow, whatever is this, probably image, image show. And plot title sets the title of the subplot to feature name. And what we can say about our visuals, as you can see, setting 1, setting 2, and S2, and here S3, and etc. Recurrence plot is a visual representation of when a state in dynamical system recurs, and in this context it shows the similarity of sensor readings over time. And each plot is a PT-FIT matrix, and where the color intensity represents the distance between sensor readings at different time points, and brighter, what we can say, brighter spots indicate higher similarity between those points in time. And what we can say additionally, by transforming time series into images, the model can leverage convolutional neural networks to detect complex patterns that might be missed by traditional time series analysis, and this enhances the model's ability to predict remaining useful life and detect anomalies. And also recurrence plots can help identify patterns and trends in the sensor data that precede engine failures. And for example, consistent recurrence patterns might indicate normal behavior, while disruptions could signal potential issues. And I hope you understood that part. And let's talk about another cut blocks. Here, extrain and ink. What is this? Here we transform training data to images, and let's look at these parts. Okay. Here we convert the training data sequences into recurrence plot images, and have about the process. NP apply along axis and the parameters applies the recurrence plot function along the second axis of the X-train array, transforming each sequence into a recurrence plot. And dot S type, what is this? And plot 16, it converts the resulting image to the plot 16 data type for efficient storage and computation. And here X-ray image shape here it becomes an array of recurrence plot images derived from the training sequences. And here X-test image same things as you can see here. And let's look at our outputs. The training set consists of 15,006 31 images, each size of 50 pixels with 17 channels, and the test set consists of here 8,162 images, each of size 50 pixels with again 17 channels. And I think it's okay. And here seed set part, and you know that part actually. Anyway, it ensures reproducibility by setting the seed for various random number generators. And what happens to tf.random set seed? It sets the seed for TensorFlow's random number generator, and also environment and Python hash seed. What is this? It sets the environment variable Python hash seed to specify seed value, ensuring consistency in Python's hash-based operations. And np random seed sets the seed for NumPy's random number generator. And random seed sets the seed for Python's built-in random number generator. And I think it's okay, so we can look at our model part here, and we can talk. Let me see a little. Okay, what happens here? Model equal sequential. It initializes a sequential model, which means the layers are added sequentially one after the other. And let's look at this part here, second part. Convolutional, I mean here conv, it's convolutional 2 dimensions or 2D. What is this? The two convolution layers with 32 filters, each with a kernel size of here 33. The activation function used is ReLU, which introduces non-linearity to the model, and max pooling 2D, I mean 2 dimension. A max pooling layer with a pool size of to reduce the spatial dimensions of feature maps, helping to reduce the computational load and control overfitting. And dropout layer, a dropout layer with a rate of 0.25, which randomly sets the 25% of the input units to 0 during training, further helping to prevent overfitting. And let's look at the second convolutional block, and what happens here. Similar to the first block, but with 64 filters, as you can see here. in each convolution layer, allowing the model to learn more complex patterns. And here we have a fully connected layers. And what is the flatten layer? Flattens the three-dimensional output of the convolution layers to a one-dimensional vector. And that layer here, a fully connected layer with 256 units and ReLU activation, and a dropout layer with a rate of 0.5, which sets 50% of the input units to 0 during training, and output layer, a dense layer with 3 units and softmax activation, which outputs the probabilities for each of the 3 classes. And we'll compile the model, and you can see the summary and what we can say. Alright, let me switch a little. Okay, each convolutional two-dimensional layer applies filters to the input data to extract features, and the number of parameters is determined by the size of the filters and the number of filters. And max pooling max pooling layers. These layers reduce the spatial dimensions of the data, helping to condense the feature maps and reduce computation load. And dropout layers here. These layers help prevent overfitting by randomly setting a fraction of input units to 0 during training. And what we can say here, flatten layer. This layer converts the three-dimension tensor output from the convolution layers into a one-dimensional vector, and dense layers, fully connected layers that apply learned weights to the input data to make final predictions. And the output shape here indicates the dimensions of the data as it passes through each layer, and the number of parameters shows the complexity of the model, and the total number of trainable parameter is 1 million and 300,000, and here it's a large value. And why we built this architecture? This architecture leverages the power of convolution layers to extract spatial features from the recurrence plots, and the fully connected layers at the end use these features to make predictions about the remaining useful life of the engine. And I think so can, I think we can switch, and let's talk about these parts. What happens here? Here set seed 33. It ensures reproducibility by setting the random seed for various libraries, and it makes sure that the training results can be consistently reproduced. And as early stopping, monitor well accuracy, etc. What happens here? Here monitors the validation accuracy during training and stops training early if the performance on the validation set stops improving. And what are the parameters? First, monitor equal accuracy, monitors the validation accuracy, and mode auto. What is this? Automatically determines whether to minimize or maximize the monitored quantity, and restore best and weights equal true. What is this? It restores the model weights from the epoch with the best validation accuracy, and verbose one provides updates during training, and patience 6. Number of epochs with improvement after which training will be stopped. And here we will fit the model, X-train image, training data, Y-train training levels with 1 hot encoded, and batch size here 512, number of samples per gradient, and epochs 25. Number of epochs to trained model, and callbacks here, list of callbacks to apply during training, and validation split here, fraction of the trained data to be used as validation data, and verbose to verbosity mode. And you can see the our output and what happens here. For example, epoch 1 training loss and training accuracy, validation loss, validation accuracy. The model starts with a moderate accuracy, indicating that is learning from the data but has room for improvement. And what we can say for epoch 2, slight improvement in training accuracy, but validation accuracy remains the same, suggesting the model is still learning. And let's look at, for example, 5. Significant improvement both training and validation accuracy, indicating that the model is effectively learning patterns from the data. And let's stop in the epoch 10 here. The model continues to improve with high accuracy on both training and validation sets. And let me switch and epoch 15. What we can see here, the training accuracy continues to improve, but there is a slight increase in the validation loss and a decrease in validation accuracy, suggesting possible overfitting. And here epoch 16. Early stopping is triggered as the validation accuracy has not improved for several epochs, and the model restores the best weights, ensuring the highest validation accuracy is achieved. And let's look at the model evaluate. And what is this? To evaluate the trained model on the test datasets, and you can see parameter x test image, y test, and verbose equal to. It is verbosity mode for logging. And what we can say, loss here. A lower value indicates better performance, you know that, and accuracy, the proportion of correctly classified instances among the total instances in the test data, and accuracy of 78% indicates that the model correctly predicts the labels for about 79% of the test instances. And let's look at the another function here, plot confusion matrix, and what happens here. First, CM equals CM S type. It converts the confusion matrix values to proportions for better interpretability. Okay. And let's look at this part, plot info, and what happens here. A visual representation of the confusion matrix, and plot info displays the matrix as an image, and title, you know that, and x-statics and plot y-statics, what are they? Sets the labels for the x and y axis, and fmt, and what is this? What happens here? Here it adds the text annotations to each cell in the confusion matrix for clarity. And what we can say here, format CMIJ what is this? It formats the matrix values, add plot text, and what is this? Places the text within the matrix cells, and color, what is this? And equal white if CMIJ trash as black, sets the text color for readability. And here we label axis, and I think it's okay. So I think we can switch to our final part, and here what we can say and what happens in the final. Here print classification report and p where what happens. This code generates a classification report for the test data. The classification report function provides precision recall, advanced score, and support for each class, and it compares the true labels with the predicted labels from the model, as you can see here. And CNF matrix, what is this? This code calculates the confusion matrix, which is a summary of prediction results. The matrix shows the number of correct and incorrect predictions categorized by each class, and the plot confusion matrix function visualizes these matrices for better interpretability. And what we can say for our output. For example, here our classification report, class 0, high precision but lower recall, indicating that while almost all predictions for class 0 are correct, some actual class 0 instances are missed. And class 1 here, low precision and but high recall, indicating many false positives but fewer false negatives. And class 2, moderate precision, low and very high recall, indicating a significant number of false positives but very few false negatives. And overall accuracy is 0.79, meaning the model correctly predicts 79% of the instances, and the macro average provides a balanced metric across all classes, while the weighted average accounts for the class imbalance. And let's look at the confusion matrix and its diagonal elements represents correct predictions. Higher values indicate better performance, and off diagonal elements represents incorrect predictions. Lower values are better. And you know that class 0, 78% of class 0 instances are correctly classified, while 22% are misclassified as class 1. And class 1 values and class 2 values. And what we can say for final, the model shows a good overall accuracy of 79%. However, there are some points to consider. The precision for class 1 and class 2 is relatively low, indicating that the model struggles with false positives for these classes. And the recall for class 0 instances are not being identified correctly, and the confusion matrix highlights that class 2 has the highest recall, meaning almost all instances of class 2 are correctly identified. And that's all for our CNN lesson. Thank you so much for your listening. And as homework, you can improve the results and outputs and values here. And see you in the next class. Goodbye.